Thanks. Yes, this project started at the time of my PhD thesis and is still under development, especially for optimizing various initial conditions of the code. And yes, the code is Gadget 3 and is a code for cosmological simulations. The first attempt to bring it to the GPUs was during the EuroHack event, hackathon of 2015 in Lugano. Yeah, so let's see. Yeah, we first talk about the code, then our porting approach, that overlaps computation between GPU and CPUs, some tests, and then finally the latest results that I'm trying with initial conditions that are so-called to mean, so a very deep tree structure of the data. So the code for cosmological simulation is a so-called n-body code. So basically, we are dealing with particles, with positions and velocities, and we have to compute forces between particles. Particles are organized in a tree, and the gravitational interaction is computed by a relatively famous algorithm that is called Banksat, plus a particle mesh approach for long-range interactions. And those two effects are combined together to compute the gravitational interaction. Cosmological simulations do have hydrodynamics of gas, that is involved with a technique called smoothed particle hydrodynamics. And plus there are other physical processes, but let's say what is in common with all the processes is the fact that you have the particles with positions, and those particles are organized in a tree. And to know the interaction that acts on a particle, you have to perform a tree walk and find all particles within a certain searching sphere, and then you can compute the interactions between a given particle and the neighboring particles that we found with a tree walk. I would say at first, at our first EuroHack, we were a bit afraid that the fact that the code makes so heavily use of a tree walk would have been a problem importing the code to GPUs. But we gave a try to it, and actually we found a speed up on GPUs anyway. So yeah, then let's talk about initial condition of a problem, because it's mainly about tree walks and computing interactions between particles that you found with a tree walk. You can have cosmological simulations that lives in a relatively homogeneous environment, and for your tree it means that you have typically less than 10 of tree levels to walk. Or you can have unique simulations where with the same number of particles packed in a very smaller volume and a much larger tree structure. Okay, so let's have a look at the typical portion of pseudocode that the code will execute to compute the interaction. Okay, so first of all, very important, the code is already parallel with NPI and OpenACC. And what we do is to load the balance between various computing nodes with NPI. Then every node will compute the interaction for every active particle by means of OpenACC. By the way, some codes that deals with particles, they have the so-called ghost particles. So you send particles of a different NPI rank to another NPI rank that may have to communicate with those ghost particles in advance, and Gadget doesn't do it. It performs a tree walk for every local particle in its own NPI rank. And then if these particles have to communicate with a region of the volume that belongs to a different NPI rank, you flag this particle to be exported. And by the way, this is a blocking, a thread blocking operation. And then after the tree walk of all particles, you will send and receive the particles that must be exported between NPI ranks. And meanwhile, you are doing the tree walk, and you will also find the neighbors of your target particle that stays in the local computing node or in the local MPI rank if you have multiple MPI ranks per computing node. And once you collected enough neighbors, you will perform the interaction between your target particles and the neighbor. So after the tree work, for all particles that you have in your MPI rank, you will have a blocking MPI send receive. In the same way, you will receive particles from an MPI rank that is interacting with a portion of volume that belongs to the current MPI rank. You will receive some particles, you will work with the tree, the local tree for the received particles, and compute the acceleration as we did in the first phase. Then you send results back and sorry, I was counting with the mouse the various parts of the code, but now I realize I had to use the laser pointer. So we have a first phase where we work the tree for every particle. And for every particle, we have to do a tree work. Basically, I'm repeating with the laser pointer briefly. In the tree work, we collect the neighbors, or we flag a particle to be exported if the tree points to a region of the volume that belongs to a different MPI rank. Then we do send receive of particles, that is a blocking operation, and we receive guest particles where we compute interactions on it. So there are many problems that I tried to list here. So first of all, you don't want to lose optimization in a GPU porting. Then the code has a number of active particles that will vary because it has an adaptive time step. So sometimes you can have 10 active particles over a total of 10 to the 9 particles. And so if you have only a loop over 10 particles, this loop may not perform very well on a GPU, who knows? And the entry walls are not well known to suit on GPUs. And then you have blocking operations, both OpenMP operations in the GPU version and MPI operations. So how do we deal with it? Other challenges, structures are very heavy and they break the cache. So this poses limits on the vectorization of the code. We have a blocking MPI communication in the middle of a time step to exchange the guest particles between MPI ranks. There may be time steps with very few active particles that won't fully exploit the GPU parallelism, thread blocking operations, and another problem that I didn't mention is that at least when we were doing things at CSCS, you will have a node with a very large RAM memory that in principle will fill much more particles than the equivalent if you were running the whole problem GPU. I mean, if you have a problem that has maybe 10 to the 9 particles, if you are running on the CPU, you will lose, you are going to use a smaller number of computing nodes than the possibility if you are using, if you are running all the problem on the GPU, then you have less memory and you will have to use more computing. And then the latest problem was the general effort of developers that is still ongoing, and this was the main reason we chose an OpenACC. We were not going to rewrite anything, we were not going to rewrite most of the code, and yeah. So how we dealt with the fact that GPU has smaller memory than the host memory. Yeah, for instance, I show you an example of a very large simulation that was run in 2015. We saw that although the total number of memory for a computing node in this simulation, for instance, that was run at LRZ, was more than 30 gigabytes of memory. If we run one module per time, each module would fit the GPUs. So the solution was to bring, we don't bring all the problem to the GPU, but we bring one physical module per time to the GPU, and every time we copy in and out only the necessary data for that module. So first we do gravity, we send them to the GPU all gravity data, and we retrieve only gravity output data. And then we store the data on the CPU RAM, and then in the same time step, we send the data for the SPH or for the hydrodynamic communication interaction. So again, only hydrodynamic quantities are sent in and got back. In this way, during the same time step, we do different uploads and downloads to the GPU for every, let's say, integrator or physical module that is activated in the code. So adaptive time steps won't perform on the GPU. You may have maybe 10-ish active particles on the simulation with maybe 10 to the 7 total particles. To solve this problem, we decided that also small time beams, so time beams where we have only a very small number of active particles, we will run on the CPU. And for this reason, OpenACC come to be very useful because we could just put a if statement in the kernel, in the data region, and the code will automatically run on the CPU. And so in this way, we were able to ensure that time steps with very few particles will be able to run efficiently on the CPU. And then there is a problem of the blocking MPI communication within the same time step, because as I said, first you have to find the neighbors of the particles that are organized in a tree, but some neighbors may be on a different MPI rank, so you have to send your particles to some other MPI rank in order to be processed. For this reason, we decided to split the algorithm in two. There is one part of the algorithm that runs only on the CPU, asynchronously, and this is a tree work for every active particle that will search for all regions of the volumes that belongs to different MPI ranks, and will send its own particles to the different MPI ranks. So no communication at all, only tree works to find which particles must be exported to other MPI ranks. And on the same time, the GPU performs again a tree work for every active particle, but it's doing all physics computation, all basically intensive computation between the local particle and the neighbors on the local machine. When the CPU part that is running asynchronously receives the guest particles from other API ranks, it will send the new particles to the GPU on a new, basically, async queue. Yeah, for this reason, also OpenACC async regions come to be very useful. First, we did the GPU can only compute the interactions between particles of the local neighbors, and the CPU will do interactions also of the particles that come from a different MPI rank. But then we were able also to send this other kernel to the GPU. In this way, we could just add async one, and we will be sure that this other chunk of data will be executed right after the first kernel finished. And then the CPU code will just allocate an array of neighbors that can be very large because you don't care. I mean, it's a CPU, you can have an arbitrary number of neighbors. Maybe for every active particles, you can have maybe 500 or 300 of neighbors. But in the GPU, we cannot allocate an array of neighbors indexes for every active particles, as each core of the GPU is taking care of an active particle. We cannot allocate for every active particle in the GPU an arbitrary long array of neighbors. And so we actually elaborate the neighbors on chunks of 32. So basically, we first find 32 neighbors on the GPU, then compute interactions, then find other 32 neighbors, compute interactions, and this process is made by every core. of the GPU, which again is every core is taking care of one active particle. So every core will do a pre-work and will do the computation right after. Okay, let's go for the test. First, we did our test on a single density iteration, which means all particles were active. So easy test case. We were extremely happy. Here we can see the GPU profiling with the asynchronous computation. We have the CPU that is performing all three works and doing imply communication, and then send what it received to the GPU that will then execute the new data, bunch of data that it received. But meanwhile, the CPU is doing the pre-work to find the particles that must be exported. The GPU was already doing some computation and computing interactions of neighboring particles from the local NPI rank. The speedup was impressive of nearly 4, but okay, this was very a specific time being with all particles that were active, and also we tried, meanwhile we also tried the unified memory, and we were very happy with it because it got almost the same computing time, a bit less, but not, I mean, I would say within 1% the same computing time of not unified memory. Yeah, we were very happy because then you wouldn't have to bother anymore about copying of data. Anyway, let's go back to our test cases. Then we tried a full time step. In a time step, there may be a varying number of active particles, and the speed up fell back to nearly 3. This was pretty high, already pretty high. Then we did a full run speed up, and over a full run, so there are many other processes that happens in a full run: domain decomposition, pre-build, I/O, and at the very end we got a speed up of 2. Still very happy, with some modules still keeping a speed up of 3. Especially this thermal conduction that always work on all active particles. Sorry, always work when the number of active particles is the total number of particles in the simulation. That's why we get the maximum speed up. But we still got a speed up of 2. We were very happy. And in the hackathon of 2017, actually, those speed ups that I showed you were done later than this slide. In the EuroHack of 2017, we had also a glance on how the code will scale over a very large number of GPUs. So with only a time step and only of the gravitational module, we scaled the number of GPUs up to 1,000, and we found that the speed up was always close to 2. So very happy also with the scaling of the speed up. I think I have a few minutes, so I can regulate my pace.
Yes, maybe a minute or 2.
Okay, thanks. So what I'm doing now is to try to bring zoom-in simulations to GPUs. The difference with the simulations that I presented before is that they had maybe the same amount of particles, but packed in a smaller volume, where the tree has a larger in-omogeneity. So there is a larger overhead for the tree. And indeed, for instance, 10 to the 7 particles, almost 10 to the 8, with a central region that had a resolution 10 times larger than the region that is outside. And had a downgrade in the speed up and went down from 2 to 1.6. But 1/3 of the code now is running on serial parsers, the pre-build and domain decomposition, and the particle mesh. So one thing that we will have to do is in the near future is to really optimize those new parts that few years ago they were not even a problem, but now that we are running code on GPUs, they start taking a considerable amount of time, and probably we will spend some efforts in optimize those new serial parts that are becoming the new bottlenecks. But then with another zoom-in simulation, whose internal region is 250 times more resolved than the total volume, let's say, we regained a speedup in the gravitational sector that is very high. You may wonder why. Well, because in this case, the number of MPI ranks per particle was lower, so we packed more particles for MPI rank. And so what I learned from it is that I can still run zoom-in simulations on GPUs with our OpenACC code, as long as we really fill the GPUs with particles. Then we can really gain again speed up in the gravitational computation of 3. But unfortunately, the total speed up is only 1.4, and mainly because the particle mesh now is taking most of the time. Particle mesh is done with FFTW combined with MPI. So unluckily, I don't think I can use QFFT, because I think QFFT or CUFFT, or how is it pronounced, it doesn't support the MPI version of FFTW somehow. But I think my next effort may be in the direction of trying to port this particle mesh approach in the GPUs. And then we are with the conclusions. So we decided to upload one module per time to maximize the number of particles per host. We overlap the GPU and CPU computations. We tried unified memory, and we are very happy with it. We find always a total speed up of 2 with various configurations. And yeah, we now have a new bottleneck, that is the particle mesh, that is done with FFTW, that we may think how to port to GPUs. Thanks.